All right, again. So right now we are looking at 2011, this AP free response question. Let me see, it's the one with this beautiful, wonderful graph of velocity versus time. And so what it's asking us, or what it tells us, that we have this 0.4 kilogram mass. So let's highlight that. That's something that we know. It's moving a straight line under the action of a net force. Now, they don't tell us what forces is causing these net forces, they just say a net force. The graph above shows the velocity as a function of time during a 25-second interval. So at t equals 0, the object position x equals 0. So this is our graph right here, and it's velocity versus time. The first thing that they want us to do is sketch the graph of acceleration as a function of time through the acceleration versus time graph. Now, label the scale for the acceleration. So as we see, they didn't give us any numbers on our acceleration, so we have to make our own numbers. Now, the first thing that we need to do is look at the information given to us. And we see that we've got this wonderful piece of information right here, this graph. And we see that in order to find the acceleration, we need to look at the slope of this graph, because we see that slope is rise over run. Our rise is velocity in meters per second, and our run is going to be time, which is in seconds. And we see that meters per second divided by seconds gives meters per second squared, which is the unit for acceleration. So for this first part, part A, we see that our rise is a positive 10, and our run is a positive 5. So 10 meters per second divided by 5 seconds is 2 meters per second squared. Now for the second part, part B, we see that we don't have any rise. So our rise is 0. And so it's going to be 0 meters per second all over the time, which is 10 seconds. And so we get an acceleration of 0 meters per second squared. Now for this last one, we see we have a difference, because this one is rising, but this one is falling. So our rise is now a negative number, because we go from 10 to 5 rather than 0 to 10. And so we see that our rise this time is going to be a negative 5, and our run is a positive 10 seconds. So we end up with negative 0.5 meters per second. Now that we have that for each segment, we now need to graph that. Now we see that we have got this negative 0.5, and so we can't put our 0 at the very bottom right here, because we do have a negative number, then this negative would go below that 0. So let's make our 0 kind of in the middle. And because we have a 0.5, let's just go ahead and make our axis, or our label, so that we leave room for that 0.5. And so we see for this first part, part A, we have got an acceleration of 2 meters per second, and that's for the first 5 seconds. So that's why I said from 0 to 5, we have an acceleration of 2 meters per second squared. And you see I've labeled it A just as it's labeled above. Then for the second one, we've got an acceleration of 0 meters per second squared. So you see that I found my 0 and then made a line from this 5 to 15, because we see it's 5 to 15 up here as well. So that's going to be 0. Then from 15 to 25 seconds, we are going at a negative 0.5 meters per second squared, and so we're going to have that right there as well. So see how we've made our velocity versus time graph into acceleration. We see we don't really have any lines going diagonal on this. Now let's look at this next part right here. Part B is calculate the position of the object at 5 seconds. So we're just going to be looking at the area under the graph from 0 to 5 seconds. Now, we had talked about, why do we look at the area under the graph? Well, we look at the area because area of a triangle is 1/2 this base times this height. We see we've got 1/2. This 1/2 doesn't have any units, so it doesn't really matter in our units. So our base is going to be our seconds, so we have seconds, times our height, which is meters per second. And so when we multiply seconds by meters per second, our seconds cancel out. We end up with meters, which is going to be our unit for position. So meters is the unit for position. And so by doing that, so now let's put numbers into this. 1/2 our base, which is 5, times our height, which is 10. So we end up with 1/2 times 10 is 5. 5 times 5 gives us 25. So we end up with a position of 25 meters. Okay, now let's look at the next part. All right, so for part C, on which segment of the graph is the net force acting 0? So we see the net force equals ma, and it's going to equal 0 when acceleration equals 0, because we're not going to have a 0 mass in this problem. We're not going to have a 0 mass at all, but we do have an acceleration of equals 0, and we see that that is at B. So at portion B, our velocity is constant, therefore acceleration is 0, therefore our net force is going to be 0. And you can just explain that when it asks you to explain. You just say F equals ma, A equals 0, therefore F equals 0, and you just check it and get lots of points by doing that. Now for the next one, calculate the net force on an object during the first 3 seconds of motion. So let's look back. The first 3 seconds is between this 0 and 5, so we see that our acceleration in about 3 seconds is still 2. Again, we're going to say now, so again we're going to say F equals ma, but this time our m is 0.4, like it was up here, but this time our acceleration is 2. So we're going to say 0.4 times 2 gives us 0.8 newtons, and that's going to be your net force at 3 seconds. I hope this helps.